All right. Hi, AP students. Welcome to your Unit 7 AP question walkthrough for Le Chatelier's principle. I have previously introduced in class the concept of equilibrium response. So a reaction that's reversible, that is at equilibrium. How will it respond to any type of stress or change? All right. And Le Chatelier's principle allows us to predict the type of response. So if you could go to your workbook, page 1, we're going to go through question 3 as a very conceptual one. I will tell you in the description below where to skip to in this video to get to AP question level. But then we will be addressing multiple AP question level prompts and specifically only parts of it that address Le Chatelier's principle, because obviously, as we know, the long and the short FRQs are a combination of not only cross unit, but across subtopic within a unit. And since this is the beginning stages of this unit, we're only able to address parts of it. But we will be building on that later on. And so here we go through the conceptual kind of warm-up question. And again, if look in the description below if you want to skip to the time when we start talking about AP level. So here is question 3. A reaction vessel contains some amount of calcium carbonate and calcium oxide. If carbon dioxide is injected into the vessel, right, some type of container, such that it has a high partial pressure of 1.0 atm, which of the following is true? Okay, so for this question, I don't think I've introduced K equilibrium expressions according to partial pressure technically yet. But what I can say is just for background on this question is that K expression is always products, the ratio of the products raised to their respective coefficient over the reactants concentration raised to their respective coefficient. Okay. And so we can write the ratio according to not only concentration, but for gas containing reactions, we can write it according to partial pressure. So for this problem, what it's asking you is that we assume that this reaction has attained equilibrium at first, and now we're adding a stress, which is injecting more carbon dioxide. So we're increasing this specific reagent on the product side. As a result, that means we're going to see the mass of the calcium carbonate will decrease. Okay, if the mass of the calcium carbonate decreases, that means that we'd be using up the forward. This would favor the forward. The forward reaction would increase. Okay, that's what that means. B, the mass of the calcium oxide will decrease. Okay, calcium oxide is on the product side. So that means that the reverse reaction would be favored to restore equilibrium, would increase. Okay, because we're trying to get back to equilibrium, right? This reversible reaction is trying to find a new balance with the added stress. C, the partial pressure of the carbon dioxide will decrease. Okay, the partial pressure of the carbon dioxide would decrease would mean that I'm using up more carbon dioxide. So again, my reverse reaction would be favored, right? But automatically, by the way, you should cancel out C because it just told us that we're injecting carbon dioxide. So that is not even making sense. Like it defies the problem itself. And then D, nothing. The reaction is at equilibrium. Okay, again, cancel that one out immediately because you're like, well, the whole idea is that we're not at equilibrium and we're trying to reestablish equilibrium. So what we're left with is A and B. A requires that we need to fill some type of gap on the product side to drive the reaction forward. Okay. Right now, we're told that carbon dioxide on the product side increases, which actually means that our reaction is having too much product. It's like too much. So what's going to happen is the reaction is going to do B. Okay. It's going to start favoring the reverse direction because it's going to want to use up that seemingly excess carbon dioxide that's been injected. And so what's going to happen is the only way to use it up is to actually favor the reverse direction of the reaction toward the original reactants, calcium carbonate, and that would make be true, because if I favor the reverse, that means what's going to happen is my response is going to try to decrease, use up the carbon dioxide injected. And as a result, it's going to also use up calcium oxide into 1-to-1 ratio in order to complete the reverse reaction. So that's kind of your conceptual walkthrough. Let's go ahead and go down on the AP questions to page, hold on, I think it's like page 10 or 12. Okay, let's see, looking for a blue star. That tells me what problem. It's a green star. Sorry, guys. I had to go through all these problems and find what parts addressed what we know. Okay, we're going to start on page 15 is the prompt. And it's question 7, a long FRQ. We're only going to do about 3 parts for it because, again, we just haven't learned everything yet. But you're going to be able to see a little bit of how the AP might word a question that involves Le Chatelier's principles. So let me get myself kind of adjusted to this really quickly. And here we go. So what we have here is that we have some reaction between diatomic chlorine and carbon monoxide gas, and we definitely have a reversible in equilibrium reaction, okay? And we even have, by the way, its standard state reaction enthalpy value, which is, is going to be a connection to unit 6. So yay. And so we're given this data, at least this next set of data underneath this question applies to the following questions that we will be answering. So the partial pressure of the gases in the container, because they are all gases, so we have 3 types of gases, are monitored at constant temperature and recorded in the table below. So these are kind of at time 0, we see that the partial pressure for each of the following reagents are as recorded. And we say, okay, at time T8, so what's going to highlight this one? At time T8, is the rate of the forward reaction less than, greater than, or equal to the rate of the reverse reaction? And how would you know? So what you need to recognize is that at time T8, we see that the Cl2 partial pressure, here, let me go ahead and say, partial pressure of Cl2. Ooh. Oh, gee willikers. Okay, is equal to 0.4. Partial pressure of CO is equal to 0.40, all under atmospheric units. And partial pressure of COCl2 is equal to 0.60. Now, the ratio in our reaction says that we're in a 1-to-1-to-1 ratio according to the balanced chemical reaction, right? We're in a Cl2 plus CO goes to, okay, goes to COCl2. So we're in a 1-to-1 ratio. When we look at the time right before it, T7, and the time right after it, we see that the concentrations remain constant. So from T7 to T9, the partial pressures, which is an indicator of concentration, the partial pressure of the gases remain constant. So we know that the reaction has achieved equilibrium, is in a state of equilibrium. Thus, the rate of the forward is equal to the rate of the reverse as per the definition of equilibrium. So that's kind of a nice little, actually worked in conceptual question in an AP level question. So D, at equilibrium, the container holds the most molecules of which gas? Cl2 or COCl2? Explain your answer. So what we need to recognize is when we look at the data, okay, we have a partial pressure of at equilibrium, right? T7 through T9, we see that at equilibrium, PCl2 is equal to 0.40 and PCOCl2, which we're being asked to compare, is 0.60. So what that tells us is that at equilibrium, the partial pressure of Cl2 is less than the partial pressure of COCl2, which indicates that the concentration of COCl2 is greater than the concentration of Cl2. Okay? And that means, of course, that there are that and thus COCl2 has more molecules present. Right? Don't forget Avogadro's number. That would be how you would go from moles to molecules, more molecules present. And then this is just my little reminder to you that to go from moles to molecules, oops, G will occurs, moles to molecules, right? You use Avogadro's number, Avogadro's, I think I misspelled that number. So that's just kind of your little unit 1 review. Oh my goodness. Okay, and then finally, E, a student hypothesizes that if the temperature of the container is decreased. So remember, we were told originally that we were at constant temperature. So if the temperature of the container is decreased, okay, after time 9, the mole fraction of Cl2, and remember mole fraction is that like symbol like this, X over A, which is equal to N of A all over N total, right? It's basically partial pressure put into mole, but it's like the same relationship. It's like the same ratio that you would find. It just uses the mole value, okay? The mole fraction of Cl2 of the container will increase. That's what they think, is that the Cl2 essentially partial pressure or concentration will increase its contribution, okay? But the AP is generous actually in this question, and it gives you a second option. It gives you the ability to say agree as long as your reasoning matches it. So you could say, and I'll write this in a different color, purple, you could say, actually, yes, I agree. Because decreasing the temperature in a system where the volume stays constant, yes, because decreasing temp in a system where volume stays constant would lead to decrease in pressure, right? I believe that's Boyle's law. So now we're looking at this in terms of ideal gas law, right? Because these are all gases in a system. And if the pressure decreases, what we'll see is that the reaction will actually shift to increase that pressure again. So the reaction will shift, okay, toward the side with the greater number of gas moles, right? So there's more pressure in the container. So we would say that the reaction will shift toward Cl2 side to increase moles and thus pressure. Okay. And I realized actually I wrote that in the previous one, no, this reaction is exothermic. So an increase in temperature would drive the reaction. Hold on. I feel like I wrote that slightly backwards. Therefore, the mole fraction would decrease. Inputting the system is decreased. Oh, it's decreased. Ha ha ha. So wow, I misread that question. So let me go ahead and correct that this reaction is exothermic. So I misread that. So a decrease in temp would drive the reaction forward direction. Okay, thus the mole fraction of Cl2 would decrease, not increase, because Cl2 was on the reactant side. So we'd want to move it forward, and that's the way that it would be used up and decreased. Okay, sorry. Shows you how important it is to read the question and not fill in the prompt with what you think is there. So that's kind of the overview. So let me do a clarifying summary. For this student, you were asked what would happen if the temperature of the container decreased. Okay, it has found equilibrium. Now you're looking at stresses. Okay, so you would say, no, I disagree, because this reaction is exothermic. So a decrease in temperature would be like pulling out the product, the heat product, and thus the reaction would be driven forward. Then as a result, Cl2 as a reactant would be used up and therefore be present in less amount of concentration. Okay. Or you could have said yes, because the temperature decrease in a system where volume stays constant would be lead to a decrease in pressure, Boyle's law. So the reaction will then shift in a way that actually increases, restores that original pressure. And that would mean shifting to the reactant side where there's more molecules, a 2 mole presence of molecules compared to a 1 molar presence of product. Okay. And that would increase the pressure, restoring equilibrium. So either question would give you the point as long as your logic followed suit. All right, guys, that's, I believe, all I have for you on the AP question. I don't think I added any more. And tomorrow I will check that you completed these specific walkthrough problems. Have a great one. Bye, guys.